Good morning, everyone. Let me first begin by acknowledging the Gadigal people of the Eora Nation on whose land we currently stand and we meet today. I'd like to welcome you to the second New South Wales Chief Scientist Breakfast. I have to say I've been looking forward to this particular talk all year. Michael and I had a number of conversations last year, and I think we're all aware, the age of quantum is coming, whether it's quantum computing, quantum sensing, or quantum technologies in general. And I think what's really a challenge here is how we in Australia, and specifically given the strength that we have in New South Wales universities, how we capitalize on that and how we genuinely start building an industry and building applications and using these. We have a tremendous opportunity. So Michael Biercuk has been at the forefront of this. He founded one of the first companies in the area, and I think we're going to hear something about this. He's heavily engaged with many international companies, IBM, Microsoft, as well as local companies. He really is showing us the way and the opportunities that I think exist in this field. So it's going to be a really exciting talk. Sorry to roll it all on, but I think it's going to be exactly the kind of thing that we want to hear. Mike, I've just discovered when I read my notes, actually went to the University of Pennsylvania as an undergraduate. It turned out that I also went to the University of Pennsylvania, but Mike is much younger than I am, so we went there at the same time. He's now a professor at the University of Sydney in the School of Physics and undertakes a lot of his work, both commercial and academic there. So without any further ado, I'm going to welcome Michael to the stage. Thank you very much.
Well, good morning. Thank you very much, for the invitation. Thanks to all of you for coming. I appreciate that it's early and it's a glorious day when you could be out, playing golf or something. I'm extremely excited to be here, and you heard a little bit about my background in my bio. I'm a professor of quantum physics and quantum technology at the University of Sydney, where I run an experimental lab in trapped ion quantum computing. That's a kind of quantum computing. I'm also the founder and CEO of Q-CTRL, which is Australia's first venture capital-backed quantum technology company. And what I wanted to do today was obviously tell you a little bit about what we do in both my lab and in the company. I wanted to contextualize that, but I wanted to give all of you some insight into what this field of quantum technology is really about, what the potential and the promise are. And for those of you who are maybe more industrially minded or on the policy side, give you some key areas for action where I think we can really achieve the kinds of end goals that we just heard about a moment ago. And I'm so enthusiastic and excited about this, and I've actually built my entire professional career going back to my PhD in this research discipline, because quantum technology promises to be as transformational in the 21st century as harnessing electricity was in the 19th. And I don't mean that just because it's new and shiny and it's au courant. I mean it because there are deep parallels in the way, in the 19th century, we learned to access and then harness a new physical resource in the form of the flow of electricity and then put it to work. And today, we've learned to access and harness new physical resources given to us by quantum physics, the physics of very small things, and we're now learning to put that to work. And if you think that kind of argument sounds a little bit overblown, the first application of this kind of technology has already changed the world. GPS, global positioning systems, work because of atomic timekeeping. And in atomic timekeeping, we use one of these new resources. It's called quantum superposition. In the vernacular, we talk about things being in two states at once, two places at once. We use quantum superposition in order to access the very stable, very regular tick inside of atoms. And it's leveraging that new physical resource in that way that gives us location-based services. If any of us got here with Uber or Waze or Lyft, it gives us wide area networks. Zoom went IPO a couple days ago or a week ago. They leverage network synchronization protocols afforded by GPS. This is just the first application of the kind of technology that I'm talking about, and it has already completely shaped almost all aspects of our daily experience. And where we stand now is that there's a greenfields opportunity to build a completely new industry. the quantum technology industry. And Q-CTRL is a critical player in this, the company that I founded, because we take the expertise we've developed in my research career at the University of Sydney and before, when I worked at NIST Boulder in Colorado and during my PhD at Harvard. We take that expertise and we deploy it as software to solve some of the hardest problems in the field. And fundamentally, what we do is we make quantum technology useful. We make it do useful things via something called control engineering. And I appreciate that it's a dark photograph, but there is a great historic analogy here, and that is how control has shaped industries before. The photo that's probably hard to see based on how light it is in the room is of the Wright brothers. You probably know the Wright brothers as the first to fly. They were not the first to fly. They were the first to achieve manned-powered controlled flight. And that distinction, even though seemingly subtle, is extremely important, because there was an entire community of people successfully building aircraft at the time that were getting off the ground, not just the ones crashing off bridges. The Wright brothers introduced totally new viewpoints into the community based on their experience as bicycle engineers. They introduced the concepts that today we call control engineering. Concepts like three-axis control, roll, pitch, and yaw, the way we control an aircraft. They introduced the concepts of deformable airfoils, changing the shape of the wing in order to control the aircraft. Those insights built modern aviation, allowed them to do what others could not. It was control theory that made them successful. And you can play the tape forward to today, where the same story has played out in autonomous vehicles, in walking robots, in drones and quadcopters. Those quadcopters have been around for decades, but it's been advances in control engineering that have made them as ubiquitous as they are today, for good and for ill. Q-CTRL, based on our expertise in quantum control engineering, is looking to build this new industry as well. Now, what's exciting, if you look at this from the perspective of, say, an investor, is the kind of top-down, what's called TAM analysis, total addressable market. And the numbers are just astronomical, because Q-CTRL in particular is not levered exclusively to this one application that many of you have probably heard about called quantum computing. We are looking to be the trusted provider across all applications of quantum technology. That includes, of course, quantum computing, where we put these new physical resources to work for information processing, but also new applications in sensing, as we heard in the introduction, for defense purposes, for minerals exploration, also new kinds of medical imaging. And in aggregate, these are way over $100 billion a year markets. That's exactly what any venture capitalist wants to hear. But with this scale of opportunity, we really see that the state, as we'll talk about in a little while, is really extraordinarily well positioned to take advantage of everything that this field has to offer. Now, with that kind of run-up, it's useful to show this graph, right? Many of you are probably familiar with the Gartner hype cycle. In 2017, quantum computing appeared for the first time on the left here. The categories here are the innovation trigger, which sounds great, the peak of inflated expectations, followed by the trough of disillusionment, and then moving up to the slope of enlightenment and the plateau of productivity. You see where quantum computing has fallen here. It hasn't changed in the last iteration. We're on the innovation trigger. That's great. We haven't yet gone over that peak into the trough. But it's useful to kind of come back to reality and realize that despite our aspirations, this is a very early field. It is the deepest of deep technology. This is one of the hardest research challenges that our broad science and technical community has tried to access. If you want to try to understand why quantum technology has the potential to be over $100 billion a year in market value, why it's made it onto the Gartner hype cycle, it's useful to take a couple of steps back to try to understand what quantum technology is. And I promise I'll do this in a way that's accessible for non-quantum physicists. The place to start is with today's technology. Sometimes this is called the first quantum revolution. This photograph is a photo of microprocessors. These are the electronic devices that power our laptops, our server farms, our mobile phones. These are computer chips. And these are devices that allow us to encode and process information via the flow of electricity. And they work fundamentally because of a class of materials known as semiconductors, the most famous of which is silicon. Semiconductors are a kind of material that can either allow electricity to flow, as in a wire, or can act like an insulator blocking the flow of electricity. And they can do this and change between those two states based on the application of another electrical signal. Controlling the flow of electricity with electricity is what has given us the modern information age. It's what powers all of our technology today. And it comes to us because of quantum physics. Semiconductors fundamentally work because of quantum physics. Now, these devices are ubiquitous, and they're actually quite magnificent. The most modern versions today will have over 1 billion active switching elements called transistors in an area roughly the size of your thumbnail. I mean, that's a really magnificent technological marvel. But despite that, these really represent only the most rudimentary level of control over the quantum world. This is only scratching the surface of what quantum physics has to offer. And by analogy, it's a bit like this in terms of the way we build technology. We start with a giant pile of stuff, and by learning the right rules, we can shape that stuff into the right form. Here, a giant pile of sand, we learn the rules, and we can shape that into a sand sculpture of Freud and a patient on the couch. You can build absolutely magnificent things. Sand sculpture competitions are really quite astounding. Magnificent things just like 1 billion transistors in the space the size of your thumbnail. But it really shouldn't escape your understanding that if instead of looking at the problem and how we build technology this way, instead of looking at the giant pile of sand as our starting point, if instead we look more closely, it's easy to see that there's a new level of complexity that emerges. That instead of a kind of a homogeneous tan, the sand is actually composed of these discrete grains. Some are colored, some transparent, some opaque, some are seashell, some are stone. All of this complexity is absent when we only look at the giant pile of sand. It's only when we look closely enough that this emerges. And that same lesson carries over to the way we're thinking about building technology. We want to look more closely to find the new complexity that emerges when we look at matter on very small size scales. When we start here as our building block of technology, this is our individual grain of sand, a cartoon representation of a single atom. Because when we can see at this level and build technology at this level, new rules take over, the rules of quantum physics. And our objective in quantum technology is to take advantage of, to leverage all of that new complexity that emerges. And before any of you scoff at the notion of building technology from single atoms like this, let me show you this photograph. This is a picture, a photo of one atom in a trap in my laboratory. This is not a micrograph, this is not a scanning, tunneling, anything. This is a picture taken with a camera that's almost the same as the one in your mobile phone. What we've done is we've confined this in a special electromagnetic bottle called an ion trap. We can shine laser light on to cool the atom, and the light bounces off just like the flash from a camera bounces off your face, and we capture that in a photograph. We already have the ability to access this kind of building block, our individual grain of sand. And what's exciting from the perspective of this new technological industry is that when we get here, the picture that we have, the mental image that we have of matter breaks. And instead of thinking of atoms like little billiard balls that bounce off one another, we have to think of matter more like being composed of waves, such that atoms can spread out in space through this thing known as quantum superposition. And they can interfere with each other, like waves in the harbor. And they can even interfere with themselves. And quite amazingly, on this size scale, Nature even seems to have its own form of magic, whereby particles that obey the rules of quantum physics can be linked together no matter how far apart they are, such that manipulating one instantly affects its partner. This is called quantum entanglement. None of this is harnessed in today's technology. All of this complexity has been glossed over. And in fact, much of this physics was thought to not be real. Einstein most famously called entanglement spooky action at a distance. He thought it was a ridiculous concept. And for many decades, the kind of science that I'm talking about was relegated more or less to the dustbin of mathematical curiosities. People thought this was just too unusual, too different from our daily experience to be an accurate description of reality. But what we learned in the intervening period is that in this case, Einstein was wrong. This science is correct. This is the true version of reality. Because beginning in the 1980s, with the pioneering work of Dave Wineland, who won the Nobel Prize in 2012 and for whom I worked at NIST in Colorado, Serge Haroche in Paris, we were able to build systems that allowed us to isolate the individual grains of sand. This is a picture of an ion trap. This happens to be from my laboratory. This is the electromagnetic bottle that we use to confine those individual atoms, one to a few. And now that we know through rigorous experimentation that quantum physics provides an accurate description of reality and that all other competing theories have to be rejected at this point, the next challenge is to put this technology to work, to take advantage of, to leverage this kind of science. And so now I want to tell you about some of the ways in which we do this, some of the applications. The first that I think all of you will have heard about is called quantum computing. Who here has heard of quantum computing? Well, if you have heard about it, then maybe you'd like to understand where it came from as a field. It came from a math problem, quite amazingly. So here's a challenge I want to pose to you. Given a target number, I want you to tell me the two numbers divisible only by 1 in themselves that you multiply together to get that target number. So what are the prime factors, they're called? What are the two numbers divisible only by 1 in themselves that multiply together to give you 15?
3 and 5.
3 and 5. Well done. Let's do another one. What about 21? What are the prime factors of 21? You're on a roll. 7 and 3 is correct. So let's do one more. Right? Now you laugh because it looks ridiculous. But the reason that we were able to answer the other two off the top of our heads so rapidly is that we memorized multiplication tables when we were kids. We memorized, up to 12 times 12 generally, right? This problem is not just hard for us, it's hard for computers. In fact, this problem is so hard for computers that decomposing a number like this into its prime factors is actually the basis of all public key crypto systems, or almost all public key crypto systems. Anytime you log into your bank account with your RSA token, anytime you log onto a website and it says HTTPS, S for secure in the browser line, the security comes not because you shared some secret piece of paper with the bank. It comes because of this math problem. In 1994, this gentleman suggested that if you could build a computer that encoded and processed information using some of the new resources we find in quantum physics, resources like superposition and entanglement, that problem would no longer be hard for this new kind of computer called a quantum computer. And I think it's not hard to extrapolate the potential impact of that. If this problem of prime factorization is no longer challenging, then what happens to the security of all the information in crypto systems that we use today? Well, that was a huge motivator for the field. And even though it can be traced to earlier comments about the idea of using quantum information or quantum physics for information processing, it really was this insight that set the whole field in motion. what's important to think about for this field is that quantum computing is not just a slightly better or faster version of today's supercomputers. It's a totally different way of encoding and processing information. And you should think about a quantum computer as being as different from today's supercomputers as supercomputers are from an abacus. They're just completely different. And as a result, they allow us to solve problems that are otherwise impossible, even on the biggest supercomputers. In some cases, even on supercomputers as large as we could ever imagine building. Just to give you a tiny bit of insight into why this is so, let me show you this. This picture in the background is a picture of trapped ions from an experiment I was involved in at NIST and then again continuing while I was at Sydney. Each blue dot in the background is one atom. They naturally orient themselves in these so-called crystalline arrays because they're charged and they repel each other. Then we did an experiment where we had 300 atoms, and on each atom we encoded one quantum bit of information called a qubit, because we're not very clever at naming things. With 300 qubits and the physics of superposition and entanglement, the scaling of information in this system doubles every time we add one more quantum bit. So with 300 particles, the exponential scaling it's called, looks like 2 to the 300. That's the space of potential computations. The Hilbert space for those of you who are experts. Now 2 to the 300 numbers, all in English vernacular, represented at the same time. Not exactly what's going on, but that's as close as we can describe it. Now 2 to the 300, it's a pretty big number. 2 to the 300 is about 10 to the 100. That's a Google. It's given us the name of the company. It's a number so astronomically large that if we tried to write out on paper all of the different possibilities of these 10 to the 100 or 2 to the 300 atoms, having a 0 or a 1 on each, we would run out of matter in the universe before we could write out that number. And yet we get the same information capacity in 300 atoms that happens to live in a space less than a millimeter in diameter. Now, it's not all smooth sailing. The hard part of this is actually figuring out how to take advantage of that computational capacity. That is the challenge of a part of our field called quantum algorithm design. And I have to admit, it's not been the most successful branch of our field because people are trying to write algorithms with pen and paper, not writing algorithms on computers, because these computers haven't existed for a long time. All the same, there have been some really dramatic use cases appearing across key applications like industrial optimization, unstructured search, so you have a big needle in a haystack problem, problems in physical simulation for energy, more recently for chemistry, of course information security, as we heard before, more recently machine learning. These use cases have been highly motivational for our field. And what we've seen happening over the last, say, 5 years is a transition away from fundamental academic science over towards a new kind of industrial engagement. Where, for instance, we see both technology push and application pull leading to major progress in the field. Here is a trade rag, not from quantum physics, but from chemical engineering. Chemical and Engineering News, featuring on the cover in late 2017, quantum computing and in particular, calculations of chemical dynamics, chemical reactions, say, or chemical structure, as the killer application for quantum computing. The end users are getting very excited about the developments in this field. And at the same time, we're seeing real quantum computing hardware coming online at levels that are relevant for computations. In the last couple of years, we've seen problems in chemistry solved in quantum computers. Things like the hydrogen plus molecule. Things like lithium hydride, beryllium hydride, more recently water. Basic chemical computations performed on real quantum computers. The time is now for this to become an industry. In information processing, I'll just read you this quote. This is a quote from the National Security Agency, a 3-letter agency in the United States that's responsible for kind of cybersecurity writ large. They have an FAQ document a frequently asked questions document, in which they say the potential impact of adversarial use of a quantum computer is known and without effective mitigation is devastating to the national security suite of cryptographic algorithms. And that's a bold statement from a generally outwardly conservative organization, expressing concern about the rate of progress in this field. Now, none of you should freak out. We're still quite a ways away from breaking RSA. But things are really happening now. The time is now to move in this field. And we see that also as kind of the second key pillar in the story, that the big tech oligopolies are investing now. Going back the last 4 or 5 years, big changes in the way industry has engaged with academia. Now, most of these organizations are cloud service providers, Google, IBM, Microsoft, Alibaba. And so they're kind of telegraphing the way they envision access to quantum computing in the future. And in fact, IBM a couple of years ago put one of their quantum computers, which is small and is really a research toy, they put it on the cloud and anybody can access. Any of you right after this talk, because I know you wouldn't do it during the talk, can log on to the IBM Q machine and run real quantum computations on that machine. It is a real cloud-based quantum computer. And it changes the dynamic in the industry away from having to run a lab like I do in order to run such algorithms. These big technology oligopolies are investing very heavily. In fact, at the University of Sydney, Microsoft has invested very heavily in my colleague David Riley, who runs an effort there in associated aspects of quantum technology. And then the last pillar here is that the most remote end users, the end users who don't have anything to do with the technical research and development, but want to take advantage of quantum computing, are actively paying money today to access toy quantum computers. All of these organizations are part of the IBM Q network. Q-CTRL is also part of the IBM Q network as a provider to IBM. These are the customers of IBM. These organizations pay money right now to access IBM's most advanced, in air quotes, quantum computer. I put it in air quotes because it's still useless. It's a toy. It's a research-grade tool. But they're paying money right now to be what's called quantum ready. That's an exciting statement about the way this field is transitioning from kind of intellectual curiosity over to industry. So what is our role in this? Q-CTRL accelerates the pathway to the first useful quantum computers. We do this by solving the toughest challenges associated with what's known as decoherence, the instability of the hardware. We do this by our expertise in quantum control engineering, developed over many years through my academic research at the University of Sydney and prior. Because fundamentally, we face a really serious issue. It's kind of the Achilles heel of quantum computing in particular. That when we think about encoding information into a quantum device, here like in a cartoon representation, a single atom, over time, just by interaction with the environment, that system tends to get randomized. Comes from changes in the Earth's magnetic field, it comes from Wi-Fi, from all sorts of ambient interference. We try to focus on that. That randomization of the information in whatever our quantum device is, be it a circuit for electricity or be it a single atom, that randomization leads to errors in computing, leads to hardware errors. And the scale of these hardware errors is really something that's it's kind of a sight to behold. Here's a direct comparison. In your laptop, each transistor, each individual switching element can run at a gigahertz, that is 1 billion operations per second, for about 1 billion years before it ever suffered a hardware fault. If your computer crashes, it is always software. In a quantum computer, the same degradation happens in about a millisecond, 1,000th of a second. Now that's a kind of community average, and the difference here ranges between 24 and 27 orders of magnitude difference in the likelihood of error. This is the Achilles heel. This is what's driven almost all research in the community for decades. Q-CTRL produces something called quantum firmware, which stabilizes the hardware and addresses this problem. We extend the useful lifetime of quantum information, we reduce the likelihood of error. For those of you who are so inclined, we do this by redefining the way we perform operations in a quantum computer. Anytime we write an algorithm, we have to take that algorithm and decompose it into little operations conducted on the underlying hardware, whether it's an individual atom or some superconducting circuit. Those are things that we write down mathematically as X or Z or H that have mathematical meanings. Obviously, that has to be something physical happening at the device level. We redefine that operation such that you do the same mathematical transformation, but you also gain robustness against error. And again, we do this leveraging our expertise and the research, the fundamental research that we've done for many, many years, building a kind of scientific base for how this can work. That capability has led us to have tremendous traction in the enterprise community. So we have a number of paying customers around the world, even though we only were founded in November of 2017. We have a partnership with IBM. Accenture is a customer of ours. We have engagements with defense research agencies in the United States. We've had great traction in the media as well, which is a wonderful testament to the work that the team is doing. In March, we were listed as the #1 top quantum computing startup to watch in the world for 2019. It was a great recognition of the team's efforts again. Of course, we should take these things with a grain of salt, but it's always nice to be recognized in this way. Now, part of the recognition and part of the engagement we've seen comes from how different Q-Control is from the rest of the community. Q-Control sits in its own niche in the emerging quantum computing industry. On the left, I'm showing a bunch of quantum computing hardware startups. Companies trying to build quantum computing hardware with the names like Rigetti, Quantum Circuits, Bleximo, IonQ. They build hardware. On the right, I'm showing software companies. 1QBit, QCware, QBranch. Q-Control sits in the middle. Now those teams on the right, the software companies, are waiting around effectively for quantum computers to come into life. We have the capital efficiency of a software company because our products are software-based, but in a way that should appeal to the kind of mining background of Australia. We're a picks and shovels provider. We help enable the development of this industry by selling to the hardware manufacturers today, even before useful quantum computers have come online. We're also differentiated in the way we present ourselves. You saw this video in the beginning of opal, right? We've named all of our products after different kinds of opal, instead of quantum this or quantum that. We do that in part to be differentiated. We do that also because opals are a unique Australian gem that are globally coveted, and so are we. The first product was launched in December of 2018. It's called Black Opal. It's an online tool for developing quantum computing control solutions. It's really aimed at new users. It's aimed at helping reduce the barriers to entry for people who want to take advantage of our expertise, but don't have the background to go right into the heaviest lifting. We make a beautiful graphical interface to try and overcome those hurdles. We have other products in the market. One, Fire Opal, which is focused on sensing for defense, in particular things like standoff detection for underground hardened target detection, standoff detection for anti-submarine warfare, magnetometry, magnetic anomaly detection, and Boulder Opal, which is like the real heavy professional grade tool that allows us to integrate our solutions directly into the hardware platforms of our customers. Our ambition, as I mentioned, is to be the trusted provider of control across all applications in this space and to capture massive value from this enormous industry, with our headquarters, of course, here in Sydney. Now, some of you probably are familiar with the investors that we've attracted. I think it's worth pointing out that we've had a massive capital inflow into New South Wales from foreign investors based on our efforts to date. Main Sequence is a Australian-based VC. They led our initial round with Horizons Ventures. Horizons is the family office of Mr. Li Ka-shing in Hong Kong. a great supporter of advanced technology. And then we brought in some global heavyweights from Silicon Valley, Data Collective, a longtime investor in deep technology, and Sequoia Capital as well. But this is not something new. And this is something that I would bet most of you don't know. You might know. This idea of big capital inflows into New South Wales has not started with Q-Control and this kind of engagement at the industrial level. The same story exists in our research at the University of Sydney going back for the last 9 years, 10 years. My colleagues and I in the quantum science group have raised more than, in aggregate between us in research grants, more than about $100 million. And about 75% of that has come from the United States. That the US government has been a giant supporter of the research we've been doing, and the kind of activity we've been doing, even though it's public sector research, has been net cash flow positive into New South Wales. This is all predicated on the fact that there is a really extraordinary asset here, and that asset is the research base. Now, you can hear from my background and my accent that I am not from Australia. I'm from New York, and I left the most egotistical city in the world in order to come here because Australia is so good in quantum physics. I feel like the joke about New York was a little better than the response that I got. But I moved here in 2010 to establish my own independent academic team based on decades of investment in human capital. Decades of investment in fundamental research at universities all around Australia, but in particular here in New South Wales, where we have major research efforts now underway at the University of Sydney, at UTS, at UNSW, and Macquarie. 4 of the big kind of research-intensive universities here, all with significant plays in quantum science at an educational level. It was this kind of backdrop that attracted me and attracted my colleagues. Of my colleagues at Sydney, there are 6 faculty members now in quantum science, quantum technology. Only 1 is from Australia. The rest of us are immigrants. We've seen already that that base is being leveraged to build new industry locally. Obviously, I've told you a little bit about the background of Q-Control, and because we like to sell our own book, I make the logo the biggest. But we also have seen other industrial plays coming online. Some of them very clearly in the quantum realm. So QBranch is a kind of data analytics company based both in Adelaide and in Washington, D.C. HBAR is a consulting firm. Quintessence Labs is effectively a defense contractor focused on quantum key distribution out of the ANU. But then we also have slightly indirect plays like Liquid Instruments and Mog Labs, which are both providing advanced electronics and laser systems to researchers in our community. Now, Mog Labs and my academic team have had a collaboration for many, many years. They've provided a lot of the advanced lasers that we use, and they are now the kind of de facto supplier of laser systems globally for a lot of the trapped ion research that we do. It's already happening now. There's already this kind of motion in industry. But based on the audience, I wanted to give something that many of you who come from policy backgrounds can take photographs of, and we can talk through a little bit. It's the ugliest slide I've made in a long time. But I will talk you through this. I have made a 5-point plan for New South Wales. In particular, action to take advantage of the opportunity base that exists from all of the research strength that's been around for so long. The first point is that it's essential to recognize the full scope of opportunity and make your strategies recognizing that. It's important to not be parochial and see this as 1 or 2 researchers at 1 or 2 institutions. This is extremely broad-based, with literally dozens of senior researchers and hundreds of students, postdoctoral researchers, now entrepreneurs and technologists in this field, building as we translate from fundamental research over to industry. Any strategy needs to recognize that. I will put my hand out and say there are direct funding mechanisms whereby the New South Wales government could assist us in building this industry, because what we do is so different from what we see in other disciplines. There is no real local market to start with and scale from. We are global from day one. That also means that we're on a plane a lot, and it's expensive when you're a startup doing these kinds of things. The next point relates to research translation and IP. And I know I will offend some people in the room. I think the New South Wales government should focus on incentivizing universities to fundamentally upend their IP strategies. Commercialization offices in universities, globally, not just here, globally, focus on technology first. They build a portfolio of technologies and try to license that out. But that's not how investment works from the venture capital side. Investors invest in people. They invest in teams. And I think it would be useful for universities to shift their focus to be founder first, supporting the people who want to build companies. And the single largest impediment is licensing negotiations. Licensing negotiations happen on a timescale that's appropriate for lawyers and universities, which is several years. Startups die in months. Investors walk away when they hear that you're starting negotiations to license technology from a university. Now, maybe that's unfair, but that's reality. So I advocate something that's called a creator-owned content model, where the creator is the technical inventor, the researcher or the research team, as opposed to the institution. Now, this is not pie-in-the-sky stuff. This really exists. University of Waterloo is very famous for pushing on this in the Toronto area, and there's been huge growth in entrepreneurialism out of Waterloo based on this policy. Now, understandably, this means that universities stand to potentially lose out on revenue. And with budgets being squeezed at the federal level, that is a major concern. And so there's an opportunity for the government of the state to provide incentives to release IP such that, on average, universities win. Support every company that comes out, instead of taking the venture capital model, which is, you bet on the 1 in 1,000 that gets you 1,000,000 times return. A little bit spread more broadly can smooth that over and really help trigger this translation, this release of IP from universities into the commercial sector. The fourth point is to invest in infrastructure. Now, we've already seen this starting with the Central to Eveleigh corridor, which is a really wonderful thing. But our field, because it's so different from things like, say, fintech, requires a different kind of infrastructure. It requires advanced technical capabilities as much as it requires office space. Things like technical maker spaces, prototyping facilities, advanced machining, which is almost a dead industry in Australia. Now, we've seen from the academic sector some of this infrastructure being built and shared with the community. The Sydney Nanoscience Hub at the University of Sydney is a research facility that obviously has labs for people like me who are faculty members, but also has user facilities where anybody from the commercial sector can, with appropriate training and an appropriate agreement, access the advanced nanofabrication facilities. Facilities to build nanoscale electronic circuits, facilities to build nanoscale photonic circuits, things that are many tens of millions of dollars in investment and no small company could reasonably build themselves. They are available as publicly available research infrastructure. That's the kind of investment that the New South Wales government can make, not just in nanoscience, but in surrounding technical capabilities. I would love to see more advanced machining capability in Australia. These are the things that can let us translate scientific outcomes into new products and commercial opportunities. And the last is building via education the workforce. Now, the New South Wales government has done a great job in this recently in a way that I'll mention in a moment. But I want to be clear that building this workforce is not just building other people like me. It's not just building other quantum computing research scientists. We need a massive investment in TAFE because we need people who code, who do product design, who do product management. These are not advanced research disciplines, but these are critical aspects of the community that are in extremely short supply. And this kind of skills training is best afforded not by tertiary institutions like universities, but tertiary institutions more like TAFE. Existing skills are well supported by TAFE. I would love to see a dramatic expansion of opportunities through that sector. And of course, we also need skilled migration. I know there's a lot of concern about congestion and related things, but it's the technical creative people who build these fields. 5 out of 6 senior faculty members at the University of Sydney are immigrants in this field. Australian of the Year, immigrant from last year. This kind of skilled migration is what builds the industry, and I really would love to see more support for it. Back to that positive note about what the New South Wales government has done recently. It's exciting that this so-called Sydney Quantum Academy was funded, or the funding was announced earlier this year. This is an initiative led by the University of Sydney in partnership with the 4 major research universities in the city to build a new training center, if you will, focused on the advanced research skills required to be successful in quantum computing and quantum technology. This is great because it adds a year to the PhD. It also supports better industry engagement and networking, and so Q-CTRL is excited to be a part of this as it comes online. This is a great initiative. Q-CTRL is also excited to one day get some direct support from the New South Wales government. Hint, hint. Wink, wink. I want to leave with this note, which is one I've used before and some of you may have seen. When we think back to what are the parallels in where we are in technical development in, say, quantum technology, today we're a little bit like the 1940s, building the first electronic computers. Now this machine, the ENIAC, from the University of Pennsylvania, is the first digital electronic computer. It's the first computer that processes and stores information in a way that is mathematically or even physically the same as what we use in a laptop. Digital encoding, electrical processing. When this system was being built, the one application that was the design use case was artillery shell trajectory calculation. Nobody at the time could foresee Fitbit and Zoom. It was just too remote. And even though we have these really exciting use cases for quantum technology, problems in chemistry, problems in information security, problems in standoff detection for defense, despite that promise, the most profound impacts of new technologies are usually the ones that are least anticipated. And the same is absolutely true for quantum technology. We really are seeing a new industry emerging before our eyes, and I'm really excited to be here sharing with you the notion of how we can take advantage of this, capture value, and enable prosperity for the people of New South Wales. So thank you very much for your attention.
So I've made a note of all those 5 points. Don't worry.
Thank you.
I'll have a chat to people. We've got some time for some questions, so I'd like to open it up to the floor. Please. Sorry, there's a microphone just coming.
Australia traditionally has come up with good ideas and lost control of it historically. All your good ideas, how do we keep control and maximise the benefits to Australia?
So respectfully, you will never keep control. And you shouldn't try. You should try to maximize benefit, in my view. I think, the default position on that is usually IP, right? If you do ARC grants, you have 10 pages of discussion about how you're going to protect IP. Are you really going to win in a legal battle against Apple, against Facebook? So I think that the view of protection, of closing off, ends up just kind of burning capital and time. What I think instead is that with kind of increases in global interconnectedness and reductions of the effective distance between Australia and the rest of the world, it's easier to build these knowledge economy sectors and capture value here by employing people here, right? Now, I'm happy to stay here so long as we can continue to support the staff that we require, have the skilled migration that we need, have the support of the regulators and things, because this is clearly going to be a regulated industry in the future. There's no reason that we have to move offshore. Anytime, however, there's an attempt to grab and hold on, it's like the Shel Silverstein book, The Missing Piece. If you hold on too tight, you crush it. And so I think that there are other ways that we can capture the value for Australia, for New South Wales, for Sydney, without having to resort to any kind of protectionism or kind of tight clampdowns on IP or on technology.
Next, yeah. Grant, there's a
Very interesting talk. Very
There's a
interesting.
microphone.
Oh, sorry. Very interesting talk, Michael. As an older person, I'm reminded of the 1960s and analogies with do you regard Q-CTRL like a Fortran compiler? By the way, one of the best ones came out of the University of Waterloo, called Watford, in the 60s. So that's a connection I have. But
Great. I think it's an interesting analogy. I think we're a little bit closer to VMware. We virtualize the underlying hardware to make it appropriate for higher levels of abstraction. This idea of suppressing errors, that's only the first thing that we do. It's the lowest level of our engagement. It captures one market, which is the hardware manufacturers, but we also have a very large play at higher levels in the so-called software stack, where we're talking about engaging with the developers, the people who take quantum algorithms and have to turn them into code that runs on a quantum computer. So we sit somewhere between like Phoenix BIOS and VMware.
okay.
But Fortran compilers are
Indulge me 1 second, subsidiary small point.
Okay.
Yes, no?
Next question, yeah.
Okay.
Thank you.
Thanks for a great talk, Michael. I'm very interested in how you're driving hard on fault tolerance for these things. And you mentioned sensing type applications like defense, which I regard as pretty much like an example of quintessential probabilistic computing. You're not computing things precisely. You're simply giving indications of probability, presence or absence or something. Can you speak to us a little bit about what scope there might be in the spirit of your software focus for algorithms that drive deeper into probabilistic type computing to exploit the fact that these are actually somewhat faulty devices at present?
Okay, there's a lot in that question. Thank you. I guess the background for those in the audience who are less familiar is that there is a drive to achieve something called fault tolerance, which is a mathematical prospect that enables us in principle to build arbitrarily large quantum computers. It's important because you want to think about building really large systems, but as was suggested, maybe there are other ways to go. The other way to go is now sometimes called the NISQ era, noisy intermediate scale quantum computer. These are the devices we have today, we'll have for the next 5 years. They are not fault tolerant. And in terms of kind of probabilistic applications, chemistry is one of the best examples, because the way our field has developed, the people writing algorithms with pen and paper, they were trying to do what are called asymptotic proofs. Prove that at like some massive computer scale, you can get a really big benefit by running on a quantum computer as opposed to something else. That's quite different than just trying to get something that's practically useful. Can we get some practically relevant advantage? And in chemistry, the interesting thing is that every time we do chemical calculations, calculate the energy levels of some molecule, calculate some chemical reaction rate, or the way a fuel undergoes combustion, that is always based on an approximation. So all you need is an approximation better than the best available. That's where some of these different aspects of the probabilistic outputs in the near-term quantum computers may give some new advantages.
Time for one more question. Back there, maybe. Seems to be the nearest.
Just in terms of practicality, does Q-CTRL run on any hardware at present, or what's the timeline that you believe that we'll be looking at before it does?
Well, we have products in the market right now. We have paying customers in the form of some of those organizations I showed you a few minutes ago.
Can you maybe talk about just 1 or 2 examples of something that's actually in use?
Well, so we build these error-suppressing control strategies, and those error-suppressing control strategies then get implemented in various hardware platforms. As an example, in my academic lab, we use solutions from the Q-CTRL software package directly in order to enable the kind of quantum computing experiments that we perform. And otherwise, with these partnerships with, say, IBM or Rigetti or others, we're providing the same kinds of capabilities to help them get more performance out of their hardware. I apologize, I can't go into specifics about the commercial engagements.
So let me say, Michael, firstly, I really enjoyed the fact that, you know, you're focusing on where these things get applied. I have to say, I think probably also a lot of the nearer term things are going to be in areas like sensing and other kinds of quantum technologies. But I think it's also great for the audience here to hear just where we are in New South Wales in terms of potential commercial applications. So thank you again for your thing. I'd like you to all join with me and thank Michael. And just to assist your research, there's a quantum computer.
It's very kind.
And there's a quantum sensor for you. Okay.
Thank you.
Thank you, Michael.
Cheers.
Thanks. Good. So I just want to make mention of our next seminar on Wednesday, the 19th of June, when Professor Maria Cavalares from the Children's Cancer Institute will be talking on nanomedicine. And I also want to emphasize this continues our theme this year of really trying to bring academics to give talks who also are concerned about translation of technology into outcomes. So thank you very much. We look forward to seeing you in June.